So my name is Alex Mijatovic. I'm one of the organizers of this meeting, and it's my great pleasure to welcome you to this last session of the meeting, and welcome Kavita Ramanan, who is the final speaker, also a co-organizer of the meeting. So I think I'll just let you get it on.
Okay, thank you so much. So when I was asked to talk, usually as an organizer, I prefer not to be one of the speakers. So I just said I will do one of the, a summary of, so this is very informal. I just thought we would do sort of a wrap up of what we talked about. But as I was doing this and I looked through some of the open problems, I also came across some work which I haven't actually, it hasn't come to full fruition of mine, which I could share, but I could also not share. So I will let it go as you want. It's in the afternoon of after 5 days of very enjoyable and intense sessions. So we can play it by ear. Okay, so I just wanted to start by just looking over some of the themes of the workshop, and I am mortified already in advance if I have missed something or someone out. So please already apologize in advance. Okay, so I was thinking there were some of the themes of the workshop was one, I haven't covered the open problem sessions here so much. So it's, 2D RBMs in the quadrant, I could have said, instead of the orthant, two-dimensional orthant or quadrant. So it's surprising, it just goes to show how complex a process RBM is. I really think that after years of working on this and with many sort of very senior and reputed people working on this, there's still so many interesting and open questions here. So some of the things we heard about was Rami Attar's talk on, sort of convergence of random walks in the case when the limiting RBM is non-semi-martingale. By the way, this doesn't have to be a monologue. I don't want it to be. So please just join in and say, oh, yes, and this and that, and whatever you found that you want to take away from this place. And well, this whole slide is trivial. I was going.
You want to say it in the microphone? Well, you have been not. Yeah.
And then what's still not known is, okay, that used a lot of Markovian techniques. So what if you go behind, to instead of random walks to sort of more general renewal processes, that convergence itself in the non-semi-martingale case was sort of not at all clear. Oops. And then Christina, of course, was talking about, this was in the quadrant, but so this is not quite in the quadrant. So she was in a piecewise C1 domain. I was more like two-dimensional domains rather than just the orthant, 2D RBMs. And so, existence and uniqueness for two-dimensional piece. So back in 1994, she wrote a fantastic paper on piecewise C1 domain. So before that, Tanaka had done the normal case. Lianzhen Schnittmann sort of just did a change of variable and coordinates to make it into the oblique case, but it was all still smooth domains. You had to take care of some, interior and exterior conditions, but it was really just sort of a coordinate change of the normal case, and the proofs were very similar. But you really had to come up with new ideas when they were piecewise and, non-smooth case, which Christina did in that case already. But coming from then, it's been 20 years, and still there's something interesting to be said there and open questions there, of course, that she resolved in terms of two-dimensional piecewise C1 domains when they, and that too motivated very much by applications that are coming up from stochastic networks. So there's been this really nice, I think, confluence of applications and theory in this particular area, because they've really motivated. We're not just sort of saying, okay, I know it for C1, can I do it for C1 plus epsilon? No, it's really motivated by a problem that comes up very naturally in, in bandwidth sharing and other models. So that was done by Kang and Williams and Kelly, Lee, and Williams, and so on. Okay, so, and she also talked about piecewise cones in higher dimensions, C1 cones in higher dimensions. I'm going in the wrong direction. And then, of course, Chris also contributed to the trivial to the trivial list of with a completely non-trivial proof, which I'm looking forward to reading, of trying to get pathwise non-uniqueness in the quadrant. So, why was this? I mean, for those who don't know the background as much, if you take two-dimensional RBM and you look at, there was for a large class of problems which are completely S, it was well known thanks to the work of Ruth Williams and Ryman, Taylor, and Williams, that there is a weak solution for the SDE, so reflected Brownian motion, which means that, you have a Brownian path whose law which is reflected, in the right way, but whose law is unique, right? But we don't know that this reflected path is measurable with respect to the original Brownian motion. And so you could have, so if you think of sort of the orthant and two directions pointing aside, then you could easily have, some additional randomness coming up at the origin, which decides which way the Brownian motion should go, right? So that's when you don't have this adaptedness. You could have weak solutions, but not strong solutions, which are adapted to the Brownian motion. There's some extra randomness that's deciding how the reflected Brownian motion should continue. So whether that's true or not, we didn't know for a long time for those cases. Of course, in cases when the scorecard map is continuous, we knew everything. But when it's not, we know that the deterministic problem could have multiple solutions, but it could still be that Brownian paths somehow have pathwise uniqueness, right? Because the deterministic solutions, you could have like a linear trajectory, for example, that starts at the origin, stays at the origin, and another one that goes somewhere else. But we know that Brownian motion can't stay at the origin. So therefore, it's really not clear whether Brownian path somehow will be unique. And so there's this, we're quite something that's relying a lot on 2D to try to show that there is actually pathwise non-uniqueness. And then Sandro Franceschi also talked about explicit solutions for invariant measures of gaps of a 2D RBM, again, motivated by sort of the Atlas model and in a degenerate setting. So of course, studying invariant distributions often in degenerate or hypoelliptic settings is harder. But in fact, they were saying that some of the calculations in this case actually simplify in the degenerate setting. So it has a very full explicit solution to invariant distributions in the 2D. And before this, really, one knew things about the tails of the distributions, one thing new in this, sort of skew symmetric case, but they had a pretty complete picture along with Killian and others on, so the invariant distribution of reflected. And then, of course, the most recent talk, which I don't need to repeat from this morning, about cone points and flows. Okay. And then the next thing, we had other RBM related questions. So Hélène Guérin talked about existence and uniqueness questions when adding state dependent drifts and degenerate diffusions to Atlas models. So here the degeneracy was a big issue in terms of extending the theory. And then there were two talks on interacting sort of reflected diffusions. One was sort of not directional. I think Vadim Sherbakov was talking about convergence of heavy traffic limits of interacting queues, where queues are on a graph, and each person, the way the queues evolve or served depend on the states of their neighbors and as well as themselves. And so this is a classic interacting particle system on a graph, and then sort of convergence in heavy traffic to these interacting diffusions. And then again, Tomoyuki is more recent, so I don't have to remind you, but this is when there's directed chain, I should say, sorry, stochastic differential equations with reflection and getting explicit sort of characterizations of marginals. And of course, Madhav Murugan online told us a lot about heat kernel estimates for RBM, so other RBM related questions. So, and then Pierre-Yves Gautreau-Lamar told us about some very interesting question, which I definitely want to look at more carefully, about Feynman cup representations of certain things arising from random matrices and integrable systems. And the question is really, you can do things when you don't condition the bridges. These should be really reflected Brownian motion bridges is what I meant to say, but that is a conditioned reflected Brownian motion. So you can get these representations when you just have reflected Brownian motion, you can get nice representations. But what happens when you have bridges? Then somehow, the existing theory doesn't work. So I think that's a very, very interesting, again, like sort of a talk with an open problem. That was very interesting. And then Miha Brassard talked about the ergodicity of RBMs with joint work with Alex, with about asymptotically stable variance in tubular domains. I hope my summary is okay, is reasonable, right? So, and sort of trying to understand when sort of the earlier parts of the diffusion matter or not in terms of ergodicity properties. Okay. Then other related processes, Sara Mazzonetto talked about sticky Brownian motions and inference questions related to that. Gregory Scher talked about universality of various quantities related to rough landscapes, like the minima, the sort of till the first passage and various different things arising from general random walks and relations to the Spar-Anderson results, which Vlad has worked on. And again, the question was, so then, of course, there was applications. Again, Miha Brassard, I sort of put him in two different because he was talked about two different things. Denoising diffusions, so this is not necessarily related to RBMs, but when does sort of an Ornstein-Uhlenbeck do better when you're doing these denoising diffusions than adding multiplicative noise in terms of mixing? And it was very much related to whether you had an original multimodal distribution and then whether the stationary distribution of your process is light-tailed or heavy-tailed. And that interplay was, again, very interesting, I think. So, okay. And then Yancy talked about numerical methods, which, yeah, I think was the only representative talking about numerical methods. So I think Rami's is, in a way, a numerical method if you're trying to show convergence of discrete things to continuous objects for singular control problems that arise. And then Rama Khan talked about modeling order books at multiple time scales. And I think one of the things I found very interesting was how the empirical observations seemed to, like, he had two different models. And then, he sort of got data, was very data intensive, the data from two different models at two different time scales. So they were coming from completely different data sets. And the empirical observation was that both these models seem to predict, they seem to be consistent. Of course, I haven't looked at the details, but I think that was quite interesting. Because this is a really complex process and you have to make some idealizations in the models of order books. And so this is all the way going to sort of quite complicated SPDE models of these order books, measure flows, and still being able to actually get something out that you can say something about. I think it's quite a modeling to the force. And then Guodong Pang also talked about measure valued models of epidemics and sort of SPDEs that capture their fluctuations. Okay, so Maria Vlasiu, last but definitely not least, talked about fork join queues, supply chains, and extremes. So she also gave a lot of motivation as to why you want to study these fork join queues in various different contexts. So, okay, so that's, I hope I haven't missed anybody out. So any comments on anything so far? Okay, so that's sort of just wrapping up some of the things that we saw. And I was just saying, okay, going forth, I mean, where might we want to go? I mean, we did already do things beyond 2D, of course, and lots of things are known, but we have understood the two-dimensional cases much better than this. There's a lot more to understand in higher dimensions, like for invariant distributions, for even some existence pathwise unique questions. There's that, but there's a lot of other questions. Of course, there's so many applications which I haven't mentioned. So if anyone wants to pipe up to say anything about that, we can. Otherwise, I could talk about other things, or we could also just call it. Okay. Okay. Okay, so maybe I could say, because I'm not used to giving totally non-mathematical talks, but I don't also want to overload you at this time. But there was a lot of discussion about existence and uniqueness, of various things. And one of the approaches that maybe didn't, so of course we all know you have a reflected, constraint process, you have some domain, you have some vector field on the boundary, and this intuitive formulation is you have some process phi, which is somehow has to remain, has some specified dynamics, doesn't have to be diffusive. It could be an ODE, it could be something else inside. And then it is constrained somehow to be inside this domain in a way that's consistent with these directions on the boundary, right? That's what a reflected process is. So reflected process to begin with is not reflected. It's constrained. So, okay, starting with that misnomer. And we talked a lot more in this talk about sort of weak existence uniqueness and things, except for Chris's talk, where there was some pathwise uniqueness. But I've been, for a long time, there are just many, many disparate approaches to pathwise constructions or pathwise uniqueness studies for reflected processes. So I thought I would just give an overview. I'm sorry, because much of this might be quite trivial to many of you, but I thought I'll give an overview of sort of some of the classical methods that people use to prove uniqueness in a pathwise setting. And why does it have to be so different in each of these cases? It's always been bothering me. So let me talk about that first. So of course, we all know the one-dimensional scorecard map, you're looking for a process, a one-dimensional process, phi, psi, which starts on the non-negative real line, and you want to create another one, which is a phi, which remains in the non-negative real line, in such a way that by adding some process eta, so eta is psi, phi is equal to psi plus eta, so eta is like a pushing constraining term, which will increase only when phi is, in danger of violating its, leaving the domain, right? Violating its non-negativity constraint. And that can be captured in this way. Okay, I'm just doing continuous, so I don't have to worry about S minus and things like that. Okay, so we all know that. And so of course, just a two-line sketch of how do you prove uniqueness. You're the usual way, you start with two different solutions, and then you have two different pushing processes, let's them call delta phi, delta eta. And then, since they're two distinct solutions, there must be some t where this delta phi is strictly positive. I think Maria is usually the Oh, okay. Yes, thank you. Okay. Okay. So, you have, okay. So you have some t for which this is greater than 0. And just for simplicity, right? Like, let me just assume that before that it was always positive. Okay, so it was at 0 and then it became positive. And so that there were no crossings before, just for the simplicity of this talk. Okay, this is crazy. This is. You tried. Yes, that's the one. Yes, that's the one. Easily reversed. We're almost there. Maybe it's next to the word edit, a little bit lower, just a little bit lower, and now a little bit further. Ah, yes.
Oh, this one. Yes, and then? Click on it again. Okay. And now Control L. Here's that. Which one?
Control L. Maria's a savior. Yeah. Okay. Okay. Let's. Okay, so this is a very really simple thing. Then you know that using 1, if delta phi s is greater than 0, that means phi 2s is greater than phi 1s, but phi 1s has a non-negativity constraint. We all know that. So if phi 2s is greater than phi 1s, we know by 3 that phi 2s for the entire period was not at 0. So therefore, d eta 2s must be 0 because it couldn't have increased. And in turn, that implies, since d eta 1s is always greater than or equal to 0 because it's non-decreasing, so you know that this d delta eta s should be less than or equal to 0. But delta phi t has to be equal to delta eta t because psi is the same input, right? Okay, so then this contradicts, of course, I assume this to make the argument simpler, but basically this contradicts that delta phi t is strictly greater than 0, but this says that this is less than or equal to 0 because eta starts at 0. Okay? Okay, so the details are obviously not important. The key takeaway is that the sign of delta eta here is constrained by the positivity of delta phi or not. Okay? So that's the main takeaway. Okay. So simple proof, but okay, anyway, so there's a unique solution, and we all know it's just, I like to put this picture to tell you it's not reflected, it's constrained, Brownian motion, that's all. So this is the map, and Skorokhod in 1961 found an explicit formula, and we know that this is what it looks like. Okay, and so it's a nice Lipschitz continuous map, in fact, with Lipschitz constant too. Okay. And then given a Brownian motion, now you can use this nice map to construct one-dimensional reflected Brownian motion or more complicated reflected diffusions with Lipschitz continuous drifts in the same way, because you can apply the Skorokhod map, you get a functional SDE with Lipschitz functionals, and so you're fine. Okay, so just to say that this pathwise approach, if you have a nice Lipschitz map, then everything works quite nicely. Okay, but a related process is which we saw in the open question session as well. It's of course a Bessel process of order n in a way, because it also is something that's constrained to live in the positive negative art, and this drift becomes increasingly singular near 0. I just want to make some analogy because the 1D RBM has a, I want to think of it as something, when I say, of course, I'm using singular in the loose way that is used as sort of being an unbounded kind of drift rather than singular in the measure theoretic way. It used to bother me a lot, but now since we're using that, I'm continuing to do that, right? So I don't mean singular in that sense, but singular, I mean sort of unbounded, right, drift. So, so the RBM we want to think of is something that is actually really singular, because at 0, I can push as much as I want. So I have a sort of capacity to put almost an infinite drift there, right? So it's sort of a squashed version of a Bessel. It's good to sort of keep that in mind. Okay, and it also has discontinuous drift, because in the interior, it has a nice little B drift, and then on the boundary, suddenly it can have something. So it's sort of like your poster child for something that is discontinuous and also singular RBMs, to sort of say why they're so hard. Okay, now that was just a little comment. That was just in the 1D case. Now let's go to convex domains. So if you go to convex domains with normal reflection field, so just reminding you that my D on the boundary is now this, and this is how a normal reflection vector field is. It's, of course, when the boundary is smooth, then it is nice and single valued, but it could be multi-valued when the boundary, when G is non-smooth, right? So in that case, you have a set of directions that you're allowed to push in rather than just one. So yet another feature of the Skorokhod problem when you go to non-smooth domains is it's not just discontinuous, it's not just singular, but it's also more like a differential inclusion than actually an SDE. It has this thing that you are pushing can lie in a whole, bunch of points, not just one. So these are the 3 things that make it quite hard. So of course, this normal direction, convex and in bounded domains was first looked at Tanaka, but okay, I'm not going to make those small distinctions. So again, so you have this, so you have to sort of reformulate it because you're, the Skorokhod problem. Okay, you want to, given a psi, which, sorry, this should be in the domain, sorry about that. Then you have a phi t that should lie in the closure of the domain, starts at the same point. Then you have this pushing process. Now before in the 1D case, the pushing process was non-decreasing. So what do you say now? What do you mean by non-decreasing? Doesn't make sense. So a somewhat arbitrary decision, or not quite arbitrary, if you want, it has some value, but is to say that, okay, let me assume that eta is of bounded variation. Okay, so I assume that eta is of this pushing process is of bounded variation. And then I can denote by this eta, the total variation process associated with eta. And then I say this total variation process can only increase when phi is on the boundary, just like my eta could increase only when my phi was at 0. Okay? So my pushing process only increases in that case. And then, of course, that is eta moves in any direction, but I also have directions now on the boundary. It's not just, so I have to say which direction it goes in. And so I have to say that this is really saying which direction my eta is going in, right, at any time. And I have to say that has to be in the normal vector field at the point at which the process is. Okay, so that's the well-known multidimensional scorecard problem. Yeah, G is the open set. That's good. Yeah, G bar is the thing. Okay. Oh, thank you. Okay, so I don't want to go into the details, but how did Tanaka prove? Just to say it's, thank you so much. So again, you take two inputs, take two outputs, and then you can write your sort of delta eta squared just as a double integral in some way. And then you substitute your phi I, psi I, use the fact that this is what it means to be a normal in the normal direction. And then you can show this inequality, that the outputs are less than the sort of input differences plus some, integral over the inner product. So it's some estimates, some calculus estimates, and using the normal reflection. And of course, if your delta psi is equal to 0, then you put delta phi equals 0, then you conclude uniqueness, right? Because then you get delta phi t the whole squared is less than or equal to 0, so it must be equal to 0. Okay. So this doesn't give Lipschitz continuity like we had in the one-dimensional case. Okay, in fact, it's not Lipschitz continuous, but you do get some sort of, a little more analysis tells you it's some Holder continuity. There's some continuity of the map. Okay, okay. Now, okay, so that was reflected Brownian motion, and now let's look at Dyson Brownian motion, which was again mentioned recently. So we saw it recently, so I'm not going to spend too much time. We know this is defined by the following system of SDEs. When beta is 1, 2, and 4, it describes the evolution of k-ordered eigenvalues. But the beta, the SDE makes sense for all beta greater than 0. And for beta greater than or equal to 1, one can establish uniqueness by showing that the process lambda does not reach the boundary of the wild chamber, which is where it belongs, which is where it lives in infinite time. I mean, of course, assuming you start there, but this is not true for beta in 0 to 1. Okay, so we already heard that in the last talk. Okay, now why am I bringing this up? I mean, what has this got to do with reflected Brownian motion? No, but again, see, it's something that's constrained to live in the wild chamber, right? So it is like a reflected process, but it's not reflected, but it's being constrained by these sort of very singular drifts. Okay. So okay, so you want to sort of combine normal singularities and normal reflection. Can you do that in one framework? And indeed, you can. And it's going to be a special case of what I'm going to say later. And so that's why I'm not going into the details right now in the interest of time. But this is due to Sepa and Lapingle, though this maximal monotone operator framework goes back to the study of differential inclusions by Aubin and Celina and many other people from the Italian school. And as well as, but what Sepa and Lapingle did is they did it for ODEs and differential inclusions, which could have discontinuous right-hand sides and also singular right-hand sides. Okay, so they developed this framework, and you can show. But what Sepa and Lapingle said is that, oh well, actually our RBMs, when it's normally reflected, can also be thought of as a dynamical system that's being driven by this maximal monotone kind of thing. And they had to, of course, reinterpret some of the things which were done for absolutely continuous trajectories to things, with measures in them, like we have our d eta. Okay, so they use that, and Yes, they can do both for beta greater than 0. So yeah, so one thing is the existence. So you can have weak existence, right? And then if you want strong, they can show strong pathwise uniqueness using the maximal monotone framework. And so then you get strong existence. Okay, and so that's one of the things. This maximal monotone doesn't just give you, existence in law, it gives you pathwise uniqueness of this process. And I will come back to this because I'm going to, give a more general framework, and I didn't want to like define all of the maximal monotone and come back again. Okay. Okay, I will tell you that again, and please feel free to ask more questions. But did I answer your question? Existence is known, uniqueness, you can get pathwise uniqueness from Sepa and Lapang from this. And they did other things also, like, particles on a circle with electrostatic repulsion, similar Dyson type things with a cot singularity rather than 1 over. So yeah, they looked at other kinds of systems like this within their maximal monotone framework and the STE, but I should actually put Aubin and Selina as sort of the PDE people who do that. Okay, so that was all with normal reflection, and then I'll quickly go through. I know most people know, okay, now I can have the D, it's the same picture, but the D may not be the normal reflection field, and then it could also be multi-valued, and whenever we have this sort of polyhedral, then at the corners and it's piecewise constant, we will take the cone generated by these. So that would be this cone to be the allowed directions of reflection at that point. So that's very, very crucial, because without putting this cone over here, then you cannot define the Skorokhod equation clearly. Okay, you have to say what's happening at 0 in order to talk about uniqueness or pathwise uniqueness or anything. Okay, so okay, and again, that makes it again a differential inclusion. And so again, you can the multidimensional SP. So now, we have to just change the definition, but here there's almost nothing to be changed. The only thing that you change is that instead of the N, you put a D here, right? Like the way in which I push is now not in the normal, but it's a D. But the rest of the conditions are exactly the same. Okay, and of course, this is just an axiomatic thing. Do I have? Then you have to ask, does there exist a solution? Is it unique, etc. Right? So that's the question. But the axiomatic framework of what it means to be a constrained process with this vector field is made clear in this pathwise sense. Okay. And of course, I told you before that this is a little bit arbitrary, because what this does is if you use this to define RBMs, even when gamma is well defined, then it can preclude you from studying non-semi-martingales. And so if you use this like this, then you know that what you add here will always be something of bounded variation, so you'll get a semi-martingale. But you can actually change these conditions. I'm not going to go into that today, but I just want to just mention that you can change these conditions so that you can do a pathwise analysis of non-semi-martingales as well. But that's not my focus today. Okay, so let's go to the simple framework of Harrison and Ryman. Or so you just look in the quadrant or orthant in general, and you have this reflection matrix. So eta, the pushing, the direction vector field is given exactly like in the picture I had drawn. The piecewise constant and all edges or common is just the convex cone or convex combination of those corresponding directions of reflection. Okay, so once you have that, so it's the same thing. So R is this matrix whose columns represent the reflection direction. You assume R is invertible, and the spectral radius of Q equals I minus R. I made a normalization earlier to remind you that the diagonal of R is all 1. So Q actually has zeros on the diagonal. It's without loss of generality. So with that normalization, if you assume that the spectral radius of the absolute value of Q, by that I mean the of the coordinate wise, but here is less than 1, then really the Skorokhod problem says I want something phi t psi t plus R of psi t, where psi now, which is just R inverse of eta, is coordinate wise non-decreasing and satisfies this. So I'm just translating what the old Skorokhod problem said in this particular case. And so in this case, you can easily see how would you try to prove uniqueness now? Okay, now you can't use the Tanaka, you can't, so what do you do here? So what Harrison and Ryman did in 81 was just say, okay, if I have phi as a solution to the SP, if and only if, now you can remember R had 1 along the diagonal, so you can take psi I of t out. If you take that out, then you say, okay, phi of t is non-negative, and psi I t increases only when phi t is 0. So that's like a reflection problem, a one-dimensional reflection problem. So what they did, it's not that you have to follow all the details, but just the ideas of what went into the proof. So you can see here that each of the psi I solve an 1D SP for psi I, which also has this unknown psi j's inside. Okay, so it's a coupled system of, sort of a system, and then you can, of course, you can rewrite this because you know the gamma 0, the 1D scorecard map explicitly, and you know that you have to have this being satisfied for all I equals 1 to k. This is a fixed point problem, and so you can solve it. And exactly this nice condition on if the spectral radius of Q is less than 1, you can do a similarity transform such that the row sums are less than 1, and then you have nice contraction, and you're done. But essentially, this is a fixed point argument and a coupling of things, okay, which works only when you are on the quadrant with exactly, k directions in RK. Okay, fine. And I do want to mention that it's a contraction with respect to the Manhattan norm. That is the L infinity in each coordinate. That's going to import. Okay, but now we wanted to go beyond that and, to go more general polyhedral domains. And then, Dupuy and Ishii came up with a sort of maybe sort of abstract and maybe at first not so immediately recognizable condition, which is that there is some geometry. So they want a convex compact symmetric set B with 0 in its interior. I want to mention that that class of sets is in one-to-one correspondence with the level sets of norms in RD. Okay, so just a little comment here. But okay, so you have to take a symmetric set B, and such that it satisfies some geometric conditions based on this sort of, your direction vector. So the VIs were the directions. So, I didn't call them DIs, but the VIs are the vectors that are the direction of reflection that you're given. So the details of this are not going to be important because you're clearly not going to be able to, figure out what's happening with this geometric condition right now. All I want to say is the set B really acts like a Lyapunov set. Now, remember that's why I did the 1D and the normal case a little bit out. And you could see that where your delta eta goes, which is the difference in the pushing terms, where it can go, in what directions it can move, depends on what your delta phi is doing. Okay? Or equivalently what your delta psi is doing in some sense. So what this is it says that if you're given the set B is a geometric set that says that if I started, that is my delta psi was some C, right? I took 2 different inputs, which had uniform norm C, then my 2 pushing terms must lie in this set. A C blow up of this set. So, okay, that's all it is. So it's a way that's saying that, okay, when I go here, I can only move in this way because phi is on the boundary, or phi is not on the boundary, and eta only pushes in this direction, et cetera, et cetera. You do the math, and then you can see that you get this non-trivial geometric condition. Okay, so this set B is a Lyapunov set, and so in fact, it shows you that the scorecard map is Lipschitz continuous on its domain. So you can see that this proof is very different from that of the Harrison-Ryman, right? It's not at all of that. So there's a fixed point argument, there's a sort of analysis argument in the normal, and then there's all these different kinds of arguments. So one of the questions was, one of the things we want to look at, in a paper with Paul back in 1999, we studied the set B because it seems a little bit intractable. How do I construct a set with certain conditions? But we sort of looked at dual formulations, and there's sort of algebraic ways to, you can convert it into sort of sufficient algebraic conditions that will ensure the existence of this set. Okay, so that makes this actually much more tractable. And one of the things that came out of this was we said that in the generalized Harrison-Ryman setting that I just mentioned, where sigma, so here sigma, sorry, is the spectral radius, and now here this Q is absolute value, means coordinate-wise absolute value of the matrix, okay? If that is less than 1, then that's if and only if a set B with a particular structure, which is really like the Manhattan norm, exists. So if you want a contraction with respect to the Manhattan norm, then you have your Harrison-Riemann, which is the most natural thing to look for a contraction with respect to. But the point is, because you have this geometry, what this Dupuy-Nishi is saying is that you shouldn't just be looking at the Manhattan norm. You need to adapt the norm to your problem, their geometry. And if you do, you can get uniqueness. Okay. So we showed that this is true. And we also showed that this is not a critical value. So that the spectral radius being 1 is not like, okay, beneath that you have pathwise uniqueness, and above that you don't have uniqueness. No, you can have this even much greater than 1, and you can still have gamma Lipschitz continuous. We constructed several examples, but one of them we put in the paper of 3 dimensions. Okay. Okay, fine. So the point is that you can have different norms and then get. Okay, so now a sort of a singular perspective on oblique reflection, the last. So I have to go back, and so let me tell you, maybe anticipate what we're trying to do is now we have oblique reflection. And we saw that with normal reflection, you might have singular processes as well, and it was sort of put into one framework by maximal monotone. But now we have oblique reflection. Is there a corresponding framework to also include singular systems in that framework? And of course, Andrei Pilipenko has also done things where you sort of, or penalization methods by Snominski, a lot of people, where you actually approximate reflected diffusions by singular diffusions, right? Many people have looked at that. So is there a common framework for that? And this was joint work with my students, Steve and Sujin Kim. So for that, I have to tell you a little bit thing about Banach spaces, but Chris, don't run away. It's finite dimensional Banach spaces. Okay, so it's not infinite dimensional. Okay, so why would we, you might be thinking, why are you even talking about norms on finite dimensional spaces? I mean, we know they're all equivalent. Okay, but the metric is not, right? I mean, you might not even have a metric if you have a norm, but what I mean is if you do want to say Lipschitz contraction, if you want to say something is Lipschitz, not the metric, but if you want to say something is Lipschitz, it depends on the norm, right? The norms may be equivalent, but that's not enough, if you want to get a contraction or something. Okay, so if you take this X is some finite dimensional real Banach space, equip with some norm. And if you want to say equip some norm, think equip with a set B, like I told you, without the additional conditions. Okay, so I have this norm and I'm equipping with some convex compact set with 0 in its interior. That's a norm, symmetric. Okay. And then I will take the topological dual, which just sounds very fancy, but all it is just, continuous linear functionals on it, which of course you can again simply identify with RK again, because we're all in the finite dimensional setting, but it has another norm. Okay, so the topological dual is simply RK with another norm, X star. Okay, and I'm not going to write X star. It's easy to write it. It's just the dual set, convex dual of B. Its level set will be the convex dual of B, of whatever this norm is. So, but the duality map on X is a map from X to the dual, which is really RK to RK in our case, but such that this dual, that norm is equal to the same norm. So it's norm preserving. Okay, and also this inner product, this is the duality map, gives you the sort of the absolute value squared, the norm squared. Okay, so the duality map gives you the absolute norm squared. Okay, in general, going backward. The duality map is not necessarily unique, but if your norm is smooth, has some C3 boundary, then it is. Okay. It has many nice consequences. I, of course, don't want to get technical. I just want to give you the idea here. Okay, so there are some things you can relate duality maps to subdifferentials of convex functions. I'm not going to go into the detail, but just to telling you that you can, just like you can look at a subdifferential, which is multi-valued, you can do that here. Okay, so the last sort of notation. So now remember, we have multi-valued operators. So you have multi-valued operators. So A is a subset. You want to think of this as sort of the set of directions of reflection. right? Or the negative of it, it's going to be actually the negative cone. Okay. So A is some multi-valued operator, and then its the domain is just where it's not empty. And then you define the graph of, all these sort of X and the set of directions, and its range is, usually defined. Okay, and these are just simple things. Then you can define something called a hypermaximal accretive operator. Okay, so accretive operators are typically used in infinite dimensional spaces to study PDEs. So I mean, this is the first sort of, but here I'm sort of applying it in a finite dimensional context. So if an accretive map operator, if for anything in the graph of the operator and some duality map, it satisfies some inequality condition. Okay. So this is what an accretive operator is. It might not be clear, but you can see that these kinds of inequalities are coming up in the scorecard problem when you look at sort of different directions of reflection and things like that. Okay. And the operator is said to be hypermaximal if the range is sort of the whole space. Okay, not too important. I just want. Why are they interesting? Why are they important? But an old result of Cato from the 70s tells you that if A is hyperaccretive, then this differential inclusion for all smooth functions F has a unique solution. Sorry, I've missed out the key thing that has a unique solution. Right? So that the differential equation is well defined. So to relate this to the scorecard problem, you want to think of this A of phi of t as containing minus the directions of reflection, right? And then your F is like a deep psi of dt because they're doing it for absolutely continuous trajectories. And so that's what it's saying. For all smooth inputs, you have a nice scorecard problem. Okay, so if your thing is maximally accretive, then you will have solutions to the scorecard problem for all C infinity paths. Okay. Okay, so just to tell you what monotone operators are, which was, those maximally monotone, which I told you. With them, they look much nicer because it's just in terms of the usual Euclidean inner product, because it's just with respect to when J is the identity mapping. And that's monotone operator is just one that satisfies this. And this was the sort of result that Sepa and Lapingle used. Okay, so just to quickly summarize, you have this data, Banach space. A is a hypermaximal accretive operator. You can fix a time, fix a path, and then you can write down like a scorecard type problem in terms of this accretive operator, right? But with measures rather than just d phi absolutely continuous and things like that. If you do that, you have, phi is continuous and takes values in like G. G is the closure of the domain of the operator. And then this difference, theta, you should think of as minus the pushing term here. So it's minus eta, what we had, has bounded variation. And it satisfies, this is the condition to say in what direction I push. And I'm not expecting you to even look at that. But I'm just saying there is a condition that you can put in terms of the duality mapping that tells you which directions you're allowed to push or you're allowed to grow in, because this is not necessarily a scorecard map. This is just any dynamical system. A could be any operator. If A is the operator, which has all its, on the boundary, fine, but it could also have drifts in the interior. Okay. So if you do that, then if you assume that this thing has a C3 boundary, which is okay for many applications, then we can show that this mapping of the solution to this accretive problem is closed and continuous on its domain of definition. So closure is really nice because if you have things that are, if you can prove it for nice smooth paths, then if you have relative compactness, you have it for the entire thing. Okay. And continuous is of course great because then that gives you uniqueness in particular. Okay. So, right. So this was just to tell you that this is, when you do this, when you look at this particular case, then you can have a relaxed set. Now the question is, of course, for what directions of reflection is it actually an accretive, hypermaximal accretive operator, right? Okay, so the question is, so when you have this, can you relax the set B assumption, which you might not have noticed this earlier, I put it in red, but the original one of Dupuy and Ishii was this had to be in a neighborhood of this plane. that Niz is less than 1, then you have this thing to be 0. Here you relax it to, I only need it at 0. What that gives you is that you can have just continuity without the Lipschitz continuity. And so you have a broader class that you can cover. And so we showed that under the relaxed set B, the scorecard map is continuous on its domain using this general maximal accretive framework. And in the generalized Harrison-Riemann frameworks, this actually includes the case when the sigma is 1. Okay, I'll go quickly through the other corollaries. It incorporates the framework of Aubin and Selina as a special case, so maximal monotone normal reflection, the Dyson-Brownian motion kind of thing. You can do an SDE version of it, of course, which I didn't want to write down for you. I'm sure you're grateful for that. So then the corollary 3 is that there are multidimensional Bessel processes. For Yamada in 1986, actually came up with a multidimensional Bessel process that arose as an HT limit of a tandem Q, which has now you cannot use a maximal monotone framework. It's actually sort of an oblique singularity. And again, you can use this to show. So now this is a framework that allows you to combine oblique singularities with reflection and also discontinuities, which I'm not coming to, but there's a paper with Rami Attar and Amarjit Budhiraja, where we introduce something called the discontinuous media problem, where you just have sort of a polyhedral cone with piecewise constant drifts, which could be different. And you can ask, when do you have a solution even to the ODE or the SDE associated with that? Of course, we know from Varetnikov that you have strong existence as long as you have an elliptic diffusion, but our result allows us to have degenerate diffusions as well in that setting. And also in the ODE setting, we can extend the classical results of Filippov on ODEs with discontinuous right-hand side. So this all falls under this monotone accretive setting. So it includes discontinuities, singularities, as well as reflection. But that's sort of the key observation, and that in finite dimensional spaces, you just have to choose the right norm to understand the scorecard web. So that was a one-sentence summary of all of this, is that with the right norm, at least when you expect pathwise uniqueness, you can make more headway than otherwise. And so it's just a small step towards unification of techniques for pathwise uniqueness. Of course, lots of caveats. We used it to gain some new insight, but I actually think it may have synergies with 2 open problems that were mentioned. One is Malek, your problem, and I'd love to discuss that a little bit more with you, and Rami's problem on the free boundary. I think that by doing looking at this framework, one might be able to get things that are not monotone in the usual sense, but still maybe do something with the free boundary. But this is, of course, like a leap kind of thing. I have no idea, but yeah, even more trivial than the one that you were thinking of. Okay, so I just will end with thanking. I don't know if there are any questions on that before I move on. Okay, so I just want to thank the organizers of the whole program, all of these people who did all the hard work, Andrew, Alex, who's here, Killian, who is here, Perla, I haven't seen, so Tassi and Corina, and also the organizers of this workshop. Killian and Alex did really all the hard work, and Ruth as well, and I was just a bystander. So I wanted to really thank all the co-organizers of the whole program and the organizers of this workshop. And of course, it's leaving out all the speakers. I hope I caught everybody. I hope I didn't miss anyone. And a heartfelt thanks to the staff at INI